Okay, let's talk about the chemical reactions of these 1,3-oxazolium 5-olates as mesoionics with different kinds of reactants such as the alkynes, carbonyls and the carbon disulphide. And one thing I'm quite sure is that you people must be knowing that all these reactions are basically the 1,3-dipolar type of cycloaddition reactions. Okay, so we will be discussing all these reactions one by one. The first one you can see here is the reaction of these mesoionics with symmetrical type of alkyne molecules, right? So here you can see this is my 1,3 oxazolium 5-olate mesoionic molecule. Let me write here the 5-olate, and the second reactant which you can see here is what it is, some sort of symmetrical alkyne molecule. Okay, and by 1,3 type of dipolar cycloaddition reaction, it is giving this type of cyclic adduct here. But the reaction won't stop here at this stage because it is entropically favored in this direction by the elimination of a molecule of CO2, which you can see here, resulting in the formation of a molecule something like this, which we all know is what it is, a pyrrole type of molecule, right? So better to write it as a substituted pyrrole, right? So as far as the very first reaction is concerned, that is with some symmetrical type of alkyne, we have something in front of us that we will get a molecule of pyrrole. Okay, and once again the reaction is a type of 1,3 dipolar cycloaddition. So the mechanism will just be like the other reactions which we have discussed in our previous video lecture, right? So I will be fast in this. So basically the strategy is quite same. I will be drawing the equivalent structure for my mesoionic, because by drawing that structural representation it becomes easy for me to write down the mechanism of this reaction. Okay, and how I can do that? I can simply write it like this, means an equivalent sign here first of all, and after that I can start drawing that structure in this way, means the oxygen here, single bond, nitrogen having the R2 as a substituent, single bond R3 here, single bond, this is my oxygen having a negative charge. And now what I have to do is I have to put two double bonds here in this ring, keeping oxygen at the center. I mean like this here. So what I can do is I can put one double bond here and the second one here like this, right? And now because the nitrogen here is forming four bonds, so it is better to put a positive charge here, something like this, right? And now what I can do is I can draw the resonating structure for this, and that I can simply show it like this, the movement of electrons, such that the second resonating structure for this will be this, means R2 here, single bond, this is my R3, this will now become a single bond, oxygen here, and this will now become a double bond oxygen, and now a negative charge here at this carbon atom bearing this R3 group, and a positive charge here on this nitrogen atom. Okay, and now what I have got here is, this is my, let me write here, this is my 1,3 dipole molecule. Okay, so I have just represented this structure here, that is my 1,3 oxazolium 5-olate mesoionic, into this kind of equivalent resonating structure representing my 1,3 dipole. Okay, and now the dipole aerophile here is what it is, my symmetrical alkyne molecule, which I can show here like this, a carbon triple bond carbon having some electron withdrawing group E, which you can see here is what it is, COOCH3, right? So here also the same substituent, that is the electron withdrawing group. And now do remember the mechanism here is what it is of concerted type. So bond making and breaking will be going simultaneously, and I can show it like this. Okay, so this will start because it is a symmetrical type of molecule, so there are no issues of regioselectivity. I can show the interaction of any of these carbon atoms with my negative end of the 1,3 dipole, right? So better to show the interaction of this carbon atom here with this carbon having or bearing the negative charge. Out of these triple bond, one of the pi bond will begin to break, and one new bond formation in between this carbon atom and the carbon atom bearing this R1 group will begin to form. Moreover, this bond here will also begin to break like this, giving us a transition state, something like this. Okay, and after that what is going to happen is I can do it like this, means this will now become a carbon double bond carbon having the same groups here. These are the electron withdrawing groups, and now I can show a bond with this carbon atom having this R1 group, which is attached to this oxygen single bond, and then a double bond oxygen. Once again this carbon atom having the R3 group, and this will now form a bond with this, right? And I do have a nitrogen bearing a R2 substituent here, and that I need to join here like this, right? And now you can see here this is this cyclic adduct which we have got. In some of the cases the reaction may stop here at this stage, but it won't be stopping in particularly in this case, because there is possible one more step here, that is the removal of a molecule of carbon dioxide. And as it is a gaseous type of molecule, and we can say that this reaction is going forward in some favorable type of step. So this is entropically favorable, we can say. Yes, it is entropically favorable. So what will happen is I can show the removal of a molecule of carbon dioxide like this. I mean, these bonds will shift here, sending these electrons here like this, such that now I will be getting what? I will be getting a structure like E here, single bond carbon, double bond carbon here having this second E group, and then this carbon atom having R3, single bond nitrogen having the R2, I mean this one here, which is attached to this carbon atom having my R1 as the substituent, right? And now because these electrons are going in between this carbon and the oxygen bond, so it becomes important to show a positive sign here like this. Okay, and these electrons are going toward this carbon atom bearing this R3 substituent, so definitely a negative charge will now appear on this. Okay, and if you people remember these positive and the negative charges, these are what? These are the formal charges, and I have also discussed the formula and the strategy how we can calculate these formal charges in my first or the second lecture. I do not remember exactly where I have discussed, but it is there. Okay, I'm sure it is there in my first and the second video lecture. Okay, so we have got this thing, and after that just reshuffling of the electrons will take place, and that can be shown like this. Mean these electrons, the negative charge here, it will shift in between this carbon and this carbon, and in order to satisfy and disperse the positive charge here on this carbon atom, these electrons will be moving towards these bonds. Okay, so what we will get here is it will result in the formation of E single bond carbon here. This will now become a single bond. This once again the second E group here, and then here is present my R3 with a double bond here, single bond nitrogen having R2 single bond. This will now become a double bond having the R1 group. Okay, so what we have got here is you can clearly see this is what this is, this product molecule, and we can call it as a substituted type of pyrrole molecule, right? So this is all about the reaction of this oxazolium 5-olate mesoionic with a reactant that is what some symmetrical type of alkyne. And what is the product, by the way? It is some substituted type of pyrrole molecule. And now let us have a look on the second reaction, in which the carbonyl compound will be acting as the second reactant. And you can see here the reaction is like this. This is our mesoionic molecule. Let me highlight this. This is my mesoionic 1,3-oxazolium 5-olate, and you can see here the reactant is what it is, some sort of carbonyl compound. Exactly talking, it is what it is, a benzene ring having a CHO, means C double bond oxygen, and a hydrogen here, means a benzaldehyde molecule. Basically it is a carbonyl compound. Okay, so even in this case, with the help of a 1,3, let me write here a 1,3 dipolar cycloaddition reaction, what is happening? It is giving this type of cyclic adduct molecule. And even in this case, the reaction is not stopping here. It is moving towards the formation of this thing by the removal of a molecule of carbon dioxide, and we can once again say that it is entropically favorable step. Okay, so finally getting this thing in which the cyclic structure is undergoing some sort of cleavage, we can say, resulting in the formation of this type of acyclic molecule, and we can call it as an enamine type of molecule. Let me write here enamine, right? And why enamine? Because it contains this en double bond adjacent to what a nitrogen atom, means the amine type of moiety. So we have an enamine molecule as the final product of this reaction, and the mechanism will be like the earlier reaction. I can write here the equivalent structure first of all. That will be R1 single bond oxygen here, single bond nitrogen having this R2 single bond, this is having R3 here, single bond like this. And now I can show here a double bond oxygen with a negative charge here on this carbon atom, a double bond here, and the nitrogen here is having a positive charge, right? So this is behaving as my 1,3 dipole molecule in this 1,3 dipolar cycloaddition reaction. And basically my second reactant, that is benzaldehyde, is acting as what? As my dipolarophile. So let me write here the phenyl, the benzene ring, the carbon double bond oxygen, and this is also having one hydrogen atom like this, right? So now this carbon atom here is having some sort of partial positive charge because it is bonded to an electronegative oxygen atom which is bearing a partial negative charge, right? So here in this case the interaction is quite simple. We can say here that this negative end of the dipole will be interacting with this carbon atom having a partial positive charge, and as soon as this thing will be happening, this bond will begin to break like this in the transition state, of course, and a new bond formation will start taking place with this carbon atom bearing this R1 group, and simultaneously this bond will also begin to break, resulting in the formation of oxygen here, a carbon, phenyl having also one hydrogen like this, a single bond. This is having what? The R1 group here, single bond oxygen, and here I am having this carbonyl. Then this is attached to some carbon atom having the R3 group here, single bond once again in between this carbon and this carbon atom. And here I am having my nitrogen like this, which is having the R2 group here as the substituent, right? And after that, what is going to happen is, and basically whatever adduct here I am having, let me write here the cyclic adduct. Okay, so this is the very first step of the dipolar cycloaddition reaction, which it has given us this type of cyclic adduct. And after that, what is going to happen is removal of a molecule of carbon dioxide, and it will be going out from the system in the same way, giving what, giving a molecule like the carbon here, the phenyl. This is also having one hydrogen single bond, oxygen here single bond, this is having R1, then this nitrogen having the R2 group, which is attached to this carbon atom having R3 here, this bond here. Okay, and as these electrons are going to this carbon atom, so I can show here a negative charge like this and a positive charge, of course, like this here, right? So now what is going to happen here is, let me write here, the ring cleavage will be going to take place. And how that will be happening, this negative charge will come in between this carbon and this carbon, and in order to disperse this positive charge here which is present on this carbon atom, which is attached to this oxygen as well as this R1 group, these electrons will be shifting and helping in the dispersal of this positive charge. Okay, so that now I can write here the phenyl bonded to this CH here, this will now become a double bond, single bond R3 here, attached to some nitrogen having R2 group, this will now become a single bond, and then we are having R1 here, and this is what, this is a double bond oxygen now. Okay, so you can very well compare this structure with what I have got here on this side. It is exactly the same structure, and yes, we can call it as an enamine molecule because it contains this ene here, means a carbon-carbon double bond. It is an ene here, ENE, and this is what, this is a molecule of amine. So we can, yes, we can better call it as a molecule of enamine, right? So this is having the exact same mechanism which we have discussed so many times, even in this lecture as well as the previous video lecture, right? And here is the last reaction, and that is with the carbon disulfide molecule. You can see here reaction with this carbon disulfide is giving, first of all, the usual cyclic adduct because it is a cyclic type of addition reaction, and removal of a molecule of a carbon dioxide from there is giving this as the sole product of this reaction, right? And you can notice here that if we want to name this molecule, because it looks like a mesoionic type of molecule, we can do it like this, means instead of oxygen we are having a sulfur here. Okay, so instead of numbering it from this direction, we will be numbering it from the other direction, because in doing so, this is having number 1, number 2, the nitrogen here is getting the lower number, that is 3. If we will be going other way around, I mean from this side, the nitrogen definitely will be having number 4 here, but that should not be considered. Okay, so on this we will be having 4 here and here 5. So the name of this mesoionic as the product of this reaction starting from some other kind of mesoionic molecule, the name is what, it will be on 1. We are having what? We are having some thio. Sulfur stands for, so I'm sorry, the thio as a prefix stands for the sulfur atom, right? So on 1 we are having some thia or thio, and on 3 we are having the nitrogen, mean the azolium. So I can call it as a thiazolium, right? Thiazolium. And now on 5 I am not having a single bond oxygen negative, I mean olate, but I am having what? I am having now a single bond sulfur negative. So this will become what? This will become a thiolate, right? So let me write here the word thiolate, right? So this is the name for this mesoionic, and we can say that because we are discussing the chemical reactions of our 1,3-oxazolium 5-olate mesoionic, the reaction of this mesoionic with carbon disulfide by a reaction known as 1,3-dipolar cycloaddition gives this adduct, which upon removal of a molecule of carbon dioxide gives another mesoionic molecule, and the name is what? It is 1,3-thiazolium 5 thiolate molecule, right? So the mechanism here is exactly same. I'll say what I can do is I can write down the equivalent structure first of all, and that can be R1 single bond oxygen nitrogen double bond positive here having R2 single bond this carbon atom with R3 having a negative sign. This will now be a double bond oxygen here, and here on the other side I am having my dipolarophile, which is what it is, carbon double bond sulfur here. So the sulfur atom, because they are having a partial negative and this is having a partial positive charge, the negative end of this 1,3 dipole will be interacting with this carbon atom, and I can show the interaction like this. This bond will begin to break, this bond will begin to form here. In the same way, this carbon nitrogen bond will begin to break, finally giving me what? Giving me a structure something like sulfur single bond carbon double bond sulfur here. This will be a single bond here having R1 single bond oxygen double bond oxygen here, and then this carbon atom having R3 bonded to this, and I can also show my nitrogen like this, which is having the R2 group here, right? And now the similar or the same step will take place, that is the removal of a molecule of carbon dioxide, and it will be like this, right, resulting in the formation of what? A carbon here double bond sulfur single bond sulfur, then this R1 nitrogen having R2 here, this carbon atom having R3, and this will be having a positive charge because the electrons are going from here, and because the electrons are coming on this carbon atom, so it will be having a negative charge like this, right? And after that what I can do is I can represent whatever product I have got, I mean this thing, in some sort of an equivalent structure. And what technique I can employ here, what I can do is I can show it the negative charge is going from here to here, sending these electrons onto the sulfur atom, such that I can write here sulfur having negative single bond. This will be a double bond here, sulfur single bond R1 here. This is having R3. This is the nitrogen having R2 group. Moreover, these two electrons can go like this, dispersing the positive charge here on this carbon atom, giving a double bond with a positive sign like this. Okay, and now we can even represent this structure here in some better form. And what will be that? If you remember, if we are having this type of structure, I mean this here, and having positive sign, I can show it in this way, means nitrogen, the positive charge delocalized over whole of the ring. Okay, and the same thing is also applicable here. Instead of the oxygen, we are having a sulfur atom, so I can represent it in this way, means the sulfur single bond, this ring structure here, I mean this is having the R1, this is having R2 here, the R3 single bond sulfur negative, and a positive charge here at the center like this here, right? So you can compare this structure with this one which I have got here, and these are exactly the same structures. And as far as the reaction with carbon disulfide is concerned, it gives another mesoionic molecule, but that of sulfur, and the name is 1,3-thiazolium 5 thiolate. Okay, so I think this is all about this lecture here. So thank you so much, dear students.